I'm Hee-Jong Lee, and I'm going to explain about Yoyak static analysis framework. And let's get started. First, this is a little speaker introduction, and I have been working in the static analysis industry since 2008, and also I studied programming language theories at a graduate school, and also on abstract interpretation. And I have been developing several static analyzers, which are mostly commercial ones, so unfortunately I cannot open the source code. And I began to use Scala 6 years ago and still actively using it in everyday development. And before that, I used Objective-Camel for developing static analyzer. Okay, this is today's agenda. And for the first part, I'm going to explain briefly about static analysis. What is static analysis? And second part is about theory of abstract interpretation. It's the biggest part of this talk. And the last three part is about Yoyak framework, and it's about implementation highlights and Scala experience, Scala related experience, and a roadmap. Explain about theory of abstract interpretation is important because Yoyak is kind of genuine implementation of the theory of abstract interpretation. So understanding abstract interpretation is understanding about Yoyak. So yeah, that's important. Okay. What is static analysis? Maybe many of you already heard about the static analysis in many places. And it's about to analyze source code without actually learning it. And someone prefers to call it a white box test as compared to black box test, just debugging or testing. And static analysis is used for mainly in industry, finding bugs, or optimizing a compiled binary and calculating software metric or proving some safety properties or something. This is the example of static analysis. For finding bugs, we use technique called symbol execution. And for optimizing a compiled binary, compiler uses the technique called data flow analysis. Many of you already learned about data flow analysis in the compiler class, right? And for calculating software metric, we use just simple syntactic analysis with just simple parsing technique. And for proving safety properties, we use model checking and abstract interpretation and type system. And I assume type system is one of the instance of static analysis. This is the two important terms in static analysis, soundness and completeness. Soundness means the analysis results should contain all possibilities which can happen in the runtime. This means, for example, if static analyzer says at this point in the program there could be a bug, then it could be a bug or not. But if static analyzer issues a warning, 10 warnings about this program, then there's no more bugs in this program. That's soundness. And completeness means that if static analyzer teach us that this point is a bug, then that's real, that's not false. So that's completeness. So these two characteristics is really important in static analysis. And for the theory of abstract interpretation, theory of abstract interpretation is a sound analysis. So it keeps soundness. And it uses over approximation. So the blue box is program semantics, actual semantics. And on the approximation of semantics is just a subset of real program semantics. And over approximation of semantics is a superset of program semantics. So if we use over approximation of semantics in analysis, then the analyzer will be sound, but not complete. But when we use under approximation of semantics, then analyzer will be complete, but not sound. Okay. What is the result of this expression? Maybe one can take 30 minutes or more than 1 minute to calculate this expression without a calculator, right? But what if we do not have an interest in exact number, rather we just want to know whether it is positive or negative? Then we can calculate this expression faster, right? We can abstract the numbers in a sign, plus or minus sign, and calculate the result, and then concretize this result to the actual n. And n could be a member of the set of integers and also a negative number, right? So we take 30 seconds for the first exact result, but we only take 3 seconds for the second result. This is a kind of abstract interpretation. The important fact is that the result is inaccurate but not incorrect, but accurate enough for a specific purpose, right? And also much faster than a real calculation. Is this program safe from buffer overruns? You can easily see that in second line, variable index has a value 0. And in a while loop, variable index can have a value 1, 2, 3 to infinity. And at the last line of the program, variable index can have 0 to infinity value, right? Because we don't know how much repeat this while loop, so we can conclude that index can have 0 to infinity value at the last line. So this program may occur array index out of bound exception at the last line. This is one line summary for abstract interpretation for dummies. Roughly but soundly execute the program. But what about for brains? First, we need to precisely define what domain and semantics means in a mathematical way. And it contains a little bit of math, but don't worry. Let me introduce you a Java language. This language is artificial language and invented for just explaining the concept of domain and semantics in a mathematical formalism. So it's pretty simple language, but has all components that most imperative languages have. So this is a language. What this program means. Maybe you know this notation if you have any experience in parser or parsing combinator or something. This is a syntax definition of a Java 1 language. C represents the command, and command is n, and n is an element of set of integer. Java 1 semantic domain looks like this. N is an element in a value set. Value set is equal to a set of integers. And meaning of C, this square bracket, double square bracket represent the semantics here. And the semantics of C is in a value domain. And the semantics of n is just n, right? This is simple. 1 plus 1. This is Java 2 language. Java 2 language is defined as an operator and n. And n is also an element in integer set. And operator is one of plus, minus, and multiplication or division. Semantic domain is the same. So Java 1 and 2. Semantics, yes, this is semantics. Semantics of n is just n. And semantics of n1 plus n2 is defined as semantics of n1 plus semantics of n2, right? This is trivial. And semantics of n1 minus n2 is defined semantics of n1 minus semantics of n2. And the interesting thing here is the notation of multiplication and division. I use a notation of a star sign in left side and cross sign at right side. This cross sign is operator in a semantic domain, multiplication operator in semantic domain, and the star sign is the operator in the syntactic domain. So they are a little bit different one. Oh, we got a assignment. X equals x plus 1. This is Java 3 language. Command is, we have only one command, one possible command, assignment. And we've got a new expression. So expression can be n or x or e operator e. Semantic domain also be extended to memory. Memory is a map from variable to value. This is natural, right? If you assume that if you are implementing some kind of interpreter of a language, then maybe you decided to use memory as a map from variable to value, right? And yes, and at here, semantics of C is defined as a function, as an element of a set of functions. Its type is memory to memory, right? So Java 3 semantics looks like this. This is not as complex as it looks like. So the semantics of assignment expression, assignment statement is assignment statement takes m as an argument, it's kind of function, and returns m by updating entry x with the value of e, right? Value of the calculation from e. And n is just n, and x is, we should find entry x in a memory, right? So that's the meaning of x, and so forth. Wow. We got two more statements, if and while. So Java 4 language has 4 statements: assignment, branch, loop, and sequence. This is a complete set of imperative language, right? And also we have same E expressions. Semantic domain is the same. Yeah, semantics. We already looked at semantics of assignment. And semantics of if and while statement is also really natural, right? If the result of calculation of expression is not equal to 0, then we take C1, semantics of C1. Else, we take semantics of C2, right? And for while statements, if the result of evaluation of expression E is not equal to 0, then we iterate again the while statement, right? Interesting thing is, this is not a definition, right? It's kind of GNU, GNU is not Unix. So what GNU means? GNU is not Unix. So what GNU means in GNU is not Unix, right? At this point, we use fixed point. So the original semantics is while m, if em not equal to 0, then while again, and else just return m. And we parameterize m and move m to the right side to make a round up form, and so forth. So the final result is semantics of while c is a fixed point of lambda f, lambda m, and blah blah. So how could we know that this fixed point exists? Because the existence and uniqueness of the fixed point is guaranteed by domain theory, but I'm going to skip these details here. Okay. Abstract interpretation revisited. Abstract interpretation is about safely estimate program semantics in a finite time. Finite time is important because program can have infinite number of states, right? So we can do that in a finite time. And abstraction is not omission, guarantees soundness. And most of static analysis technique can be defined in a form of abstract interpretation. So I think data flow analysis is just one instance of abstract interpretation with a finite domain. This is a little bit difficult part, but you don't need to understand all here because we only have 45 minutes, and I put this material for just completeness of my this slide, so you can find each details in the internet later, or yeah, okay. Anyway, we already saw that what domain and semantics in a mathematical formalism, right? So I'm gonna briefly explain Galois connection, CPUs, and continuous function. Galois connection is a pair of function, alpha and gamma. Alpha is called abstraction function, and gamma is called a concretization function. So alpha and gamma should satisfy the constraint, this constraint. So we applied alpha to an element x in domain D and applied gamma right after the application of the alpha, then it should be larger than the original one. And CPO, to be a CPO, there is three constraints. There exists an order, partial order, and the bottom element should exist, and the least upper bound of all ordered subsets should exist. Lattice is a little different. In this case, LUB, least upper bound, and also greatest lower bound should exist. Okay, continuous function. Function is continuous if it preserves the upper bounds. So upper bound of x, y, and z in domain D is z. And upper bound of fx and fy and fz is fz, right? So it preserves the upper bound. Yes. This is a one-page summary of abstract interpretation in a formal way. Important thing here is there is a concrete semantics and concrete domain. This is a real program execution. And there is abstract semantics and abstract domain. This is used by the static analyzer. And these two words is connected by Galois connection. So performing analysis using abstract interpretation means calculating x hat in a finite time. X hat is fixed point in an abstract world. And if we concretize this fixed point in an abstracted world, then we can have a sound result that covers all possibilities in real world. So least fixed point LFP, least fixed point of F, is contained in the concretization of our analysis result. Yes, this is diagram, right? So the program semantics is least fixed point F in D. And we're going to calculate the least fixed point F or bigger element in abstracted world. And we can find out sound result in our original world. Okay. So is this program safe from buffer overruns? It's too simple to be questioned, but yeah, no, this is not safe because index variable can have 1 or 10, right? So if we access the buffer strs with index 10, then it will throw array out of bound exception. This is an example of interval analysis based on abstract interpretation. So I believe you are familiar with this notation by now. So memory, concrete domain memory is a map from variables to value. And value is a power set domain of integers. And this C is semantics here. I wrote this C as same as the double square bracket, right? So C can have two arguments, command and memory, and it returns memory in this kind of function. And V here is for semantics of expression, and it takes expression and memory and returns the value. So this is the concrete semantics of interval analysis. Semantics of assignment is, as we saw in the slide before, it updates the X in memory M, right? And so forth, as trivial, right? So the concrete execution of program is find the least fixed point of F, this semantic function. So we applied F from the bottom element and applied F and F again, F again, F again, until we get a fixed point. This is the real program execution. And because this chain of this chain of F can have an infinite length, so this program we cannot guarantee that this program is end at sometimes in the future. Okay, this is abstract domain. We will use interval as an abstract domain. So memory is the same, map from variables to value, and value is the interval. This is a mathematical formalism for interval domain, which is Z hat is A to B, set of A to B, and A is element in integer set of integers plus minus infinity, and B is element of set of integers plus infinity. And the constraint is A is less than or equal to B, right? This is interval. And hat C and hat B is it's same as before. This diagram shows the shape of lattice of interval domain. So we have a bottom element and 0, 0, 1, 1, 2, 2 elements. And if we join 0, 0 and 1, 1, then we get the interval of 0, 1, right? And if we calculate the lowest upper bound of 0, 1 and 0, 2, then we get 0, 2, right? Okay, this is the lattice of interval domain. This part is important because this is how analyzer actually works. So abstract semantics. In this part, important thing is that square cup sign. That is a join operator. In concrete semantics, we calculate the expression E and takes C1 or C2, one of C1 or C2 by the result of this E. But in abstracted world, we take both of results. So if C1 return X can be a 1, and C2 returns X can be a 2, then we take X can be 1 or 2, right? And while also join all the outputs of each loop iteration. Yeah. An abstract execution of a program is something like this. We apply the semantic function f to the bottom element in the abstract domain. So apply f until we get a fixed point. What if this chain has infinite length? In concrete domain, it doesn't matter because real program could not end, right? But analyzer should always end, right? So here's the point that we need a widening operator. Widening operator is a kind of triangle sign, reversed triangle sign, and it's something like a booster. So instead of applying f and ff and fff, we jumped to top or any element to yeah. So this is a concrete example. We already used this widening operator in the previous example, right? In this example, index can have 1 to infinity, right? But in real execution, it can never end. But in analysis, it should end. So we applied widening operator to 0, I minus 1 interval and 0, I interval. Then we will get 0 to infinity interval, right? Yeah. Is this problem safe from buffer overruns? To find out this, we should solve this system of equation, this system of semantic equation. And as we saw before, we are starting from the bottom element. This is the empty parenthesis, and solve these equations, so forth. So as a result, we will get indexes 1 to 10, and result is 1 to 10. So yeah, since the size of the buffer is just 10, we could not use 10 as an index, right? Whew. Yeah. Okay. Yoyak. Do not reinvent the wheel. Motivation of Yoyak is as follows. I just don't want to reinvent the wheel because from now I have been developed many analyzers, as I mentioned before, and I found that many components that static analyzer often use are reusable. And for example, CFG data types, CFG construction, CFG optimization, CFG visualization. You should implement this kind of components if you want to implement any static analyzer, right? And graph algorithms, unrolling loops, finding loop heads, finding topological order, and intermediate language data types, construction, optimization, and pretty printing. Yeah. And some of common abstract domains, integers, abstract object, abstract memory, and also some abstract semantics, assignment, invoking, evaluating binary expression, right? This is almost common in most of the analyzers. And it's perfect to be a framework because the theory of abstract interpretation guarantees that soundness and termination of analysis if users apply valid abstract domain and semantics, right? So we can make the fixed point computation engine generic. So the user supplies abstract domain D and abstract semantics F, and generic fixed point computation engine will return fixed point for us. This is an overview of Yoyak structure. The important thing here is Yoyak consists of 4 major components. It's abstract domain, fixed point computation, and abstract semantics, and IL. And most important part among those is fixed point computation. So I take the code from fixed point computation core part, and I want to condense this a little bit to easier understanding, but each line is so important, so I cannot reduce this code. So Yoyak used worklist algorithm for finding fixed points. Worklist algorithm is simple. It uses worklist and it starts from entry. Worklist is empty at the start, and it will have entry in the worklist. The fixed point compute fixed point method is will take the one entry from worklist, and then take the input memory from our abstract domain and calculating the output memory. Maybe if you have any knowledge in a data flow analysis, you can understand this framework better. So after calculating the output memory, then it will push the next work, next successors of this basic block to the worklist again, and so forth, until we get the fixed point. So Yoyak implemented flow-sensitive forward analysis already. So you just provide lattice operations, an abstract transfer function, and widening operator to use that. What is lattice ops? First, what is abstract transferable? Abstract transferable is an object that have a method of transfer functions. Transfer identity, transfer assign, transfer invoke, transfer if, transfer assume, and so forth. So you will get the statement and the input. Then you should implement this to compute the output of the analysis. So we will give this abstract transferable object to the flow-sensitive forward analysis. And of course, we have a standard semantics. Standard semantics already implemented some basic operations of assign, invoking, and returning, and calculating expressions. Transfer assign is it's natural, yeah. It evaluates the right side of the statement and assign the value to the left side of entry in the memory, right? So lattice ops, to use lattice ops, you should provide join operator and bottom and less than equal to comparator, right? So, for example, for interval domain, the join operator will join two intervals, like 0 to 1 interval and 1 to 2 intervals. If you apply join operator to that 2 values, then you will get 0 to 2 intervals, right? That's a join operator. And bottom is bottom element. You can just define bottom element for your abstract domain. And this less than or equal to comparator. Notice that the result type of this comparator is option type, right? Option Boolean. This means order can be exist or not. Yeah, because as I mentioned in CPO, the order is partial. So yeah. This is how interval domain works in a console. So assume you will define interval 1 as from 10 to 10. It's just 10. And interval 2 from minus 10 to 10. And interval 3 is minus infinity to infinity. It's kind of top element. And interval 4 minus 10 to plus infinity. Then you can calculate this plus or minus or multiplication by using defined arithmetic operations like this. Interval 1 plus interval 2, you will get 0 to 20, right? And interval 1 minus interval 2, you will get also 0 to 20. And interval 2 plus interval 3, you will get interval top, right? Because you cannot escape from top once you have a top in your operation, and so forth. Yoyak also provides standard object model, which is used for generic object-oriented language analysis. So standard object model provide some of these APIs: updates, remove, allocation, get, and static and dynamic address. Yeah, whether it is static or dynamic address, you can find. Okay. And this is how memory domain works in a Scala console. So once you define a memory domain with interval abstract domain and set of string abstract domain, then you can assign some values to variables. So local variable x can have interval of 1 to 1. You can also update local variable x can have interval from 10 to 10. Then you can borrow the join operator from memdom.ops method to calculate the lowest upper bound of memory 2 and memory 3. Then this lowest upper bound will return the value 1 to 10 for a variable x. So, okay, IL in Yoyak. Interesting thing is Yoyak just used the case class for statement, but it will override the equals and hash code to the original case class. So it's basically the equal operation to statement is basically referential, right? It's not compare the structure of the case class. It's just compare the reference of the case class. Because we can have multiple statements, multiple same statement at various place in the method, right? Okay. And IL is defined in 3 different categories. So just statement and core statement and CFG statement. Statement have all these constructors block, switch, placeholder, if, go to, and everything. But for core statements, we drop the block and switch and placeholder. And for CFG statement, we also drop if and go to. So in statement form, program looks like this. It has switch and and in core statement, switch is dropped and is transformed to if statement. And in the form of CFG statement, we don't need go to and if statement. So we drop all of this and transform if statement to assume statement. This is a complete code of a simple interval analysis in Yoyak. So we should provide 3 objects: memory DOM ops, and abstract transfer, and widening, as notated in second line. So this is a diagram of this interval analysis. So important thing is arrows. So interval analysis in the middle of this diagram is the analysis engine. Then you should provide a CFG, that's the input program, and interval analysis transfer function on the right side of the diagram, and also provide lattice operations and widening and arithmetic operations. So then you will get the fixed point result from the interval analysis engine. This is the most Scala-related part of this talk. So I found that Scala is a very good language to implement the static analyzer, because function is the first-class citizen, as you may already know, and type class supports, and algebraic data type supports, and native support for mutable and immutable values, and excellent support for parallelization. This is trivial, and all of you already heard about what is good for functional programming, blah, 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 right? So for functional programming, it is a natural way to express mathematical logic, right? For example, for optimizing CFG, insert assume, and then remove if and go to apply to allow CFG, right? And type class support. And I found that type class support we can avoid by type class support, we can avoid F-bounded polymorphism, which is the fastest way to overworking, because F-bounded polymorphism gives seriously deteriorate code readability, right? And it's very commonly happen when inheritance meets immutability. This is the example. If you want to define some trait that returns some specific subtype of that trait, you will need to pass that subtype as a type argument, right? So you always hold that concrete subtype as a type parameters. So always need the type of concrete subclass. And this is reiterate all type variables again in subclass reference, right? For trait Q united, you should reiterate all T, R, Q, G, V, this in the type parameters, right? So we need to liberate this method from inheritance, because and this is type class. We can separate the method from inheritance. So we will get the queue-like implicit values that will have push method. And in better queue-like traits, you will have good queue-like implicit value, which also have push and pop method in it. And the class Q united, you will have all these implicit values to have this push pop something something method. So by using type class and implicit values, you can reduce the length of the type parameters. In Yoyak, we use both methods in appropriate place. So for lattice operations or arithmetic operations, we use type class. And for Galois type bounds and static standard object model or something, we use just type parameters. Algebraic data types support, yeah. This is the main reason why I choose Scala and why I switch it from objective camel to Scala, because algebraic data type support is really important to express the abstract syntax tree of a program. So if we have an abstract syntax tree like the left one, then it's naturally expressed like the right side of algebraic data types, right? And also easy to navigate the abstract syntax tree by match syntax. This is trivial. Native support for mutable and immutable values. Yeah. Scala, it also supports mutable values, mutable operations, right? As compared to most other pure functional languages does not well support mutable operations. I found that in some cases, mutability is more important than immutability because memory is mutable. In real memory is mutable, right? But if we make the abstract memory as immutable object, then we should use we should iterate over all entries if we need to update some object in a memory. So if we want to update the object to new object in the immutable memory, we should first filter the entries and fold again for this immutable object, because we cannot update in place for this object. But if we make the memory mutable, then it's really simple. And I found that my last analyzer takes so long time to analyze simple program because of this. So, yeah. Excellent support for parallelization. I think, in my opinion, static analysis does not sufficiently utilize today's advancement of computing scalability, multiple machines, big data technologies, and cloud computing. And Scala has a perfect platform called Akka. So I guess we have many fun things to try with Yoyak powered by Akka. How much time do I have? Okay. This is just one example of how to parallelize the analyzer. As I mentioned before, we used worklist algorithm, so we can parallelize worklist. So each worker can pick up their work from worklist, and yeah. Okay, roadmap. This is the final part of my talk, and this is the roadmap. I want to add more built-in abstract domains. and I'm gonna optimize analysis performance soon. And I plan to visualize analysis details and build a Scala compiler plugin. But I don't know I can do these all things because we don't have much developers. So, okay. Interval domain cannot represent the relation between two variables, right? If x can have from 2 to 8 range and y have 1 to 7 range, and it produces 49 combinations of xy pairs, right? We only need these 6 points, but when we use interval domain, we will get all these squares. What if we use octagon domain? Octagon domain can represent the relation between two variables, so it's more accurate than interval domain at some points. Two interval domain is also possible, and it's more expensive but more precise than interval domain. Okay. And I want to optimize analysis performance because analysis based on abstract interpretation is actually not really fast. So if time allows, I want to add optional faster but unsound analysis. Yeah. And visualized analysis details. I have learned that it is hard to know what static analyzer is doing at a specific moment because static analyzer's behavior is very different for each input programs and often needs to inspect and compare a map with thousands of entries, right? Because the abstract memory is a kind of map from variable to values. And unable to look over big pictures by ordinary Java debuggers, so it's really hard to debug and develop. So this is one example from SetSolver. SetSolver is not a static analyzer, but there was a project called DPViz. The project is about visualization of a search tree generated by SetSolver. So it gives some inspiration and overview of how SetSolver works. So this is the final part, and a build Scala compiler plugin. Programming language researchers foresee that the semantic program analyzer will be merged into compiler system in the near future, as type system did. So we got the syntactic analysis and grammar checking long before ago, and we got the type system a few decades ago. And now it's time to equip the semantic analysis in a compiler system. So Scala compiler is well modularized and cleanly coded, of course, as compared to other compiler systems. So excellent platform for experimenting new ideas like this. And I found that pure Scala code is safe from null, right? Once you don't write null at all in the code, right? You can use option types instead of null. However, when it linked to any existing Java libraries, it's not safe anymore, right? So I think it would be great if Scala compiler can detect possible null references from legacy Java libraries at a compile time and issue a warning. So this is one possible roadmap of this project. Okay, thank you for listening. And if you have further questions, please mail me, or I'm gonna walk around this place. So ask me. Thank you.